Now that we've discussed the system call interface provided by the kernel, let's also have a look at the system programs that run on top of the kernel. System programs are typically provided by the operating system vendor, uh, and they provide a good environment for the programmer and also for the regular users, either to develop software or make use of the software provided by other software providers. So the system programs typically provide utilities for manipulating the file system, like creating files and directories, whatever, status information, file modification, support for programming, loading the programs and being able to run the programs, communications, in other words, networking, and background services, and finally the application programs. From the point of view of most of the regular users, the operating system can be defined in terms of these system programs, because that's what the users can touch, make use of, not the actual system calls, because typically the regular programmers do not make use of the system calls. So as we said, the system programs provide a convenient environment for development and execution. So the examples are, in terms of file management, as we said, you should be able to create, delete files and directories, copy them, rename them, be able to print them, dump whatever is available, and list files or directories, the overall file system structure, and be able to manipulate these files and directories as necessary. You can also have system programs that provide status information, which is generally the general information about the operating system or your environment. Like you can get the date and time, how much memory you have available on your in your main memory, and similarly on the disk, the number of users, who the users are currently logged into your system, if we're talking about a multi-user system. Also, looking at the performance metrics of the operating system, especially when you're experiencing problems, you would like to see how much memory is available, what's the CPU utilization ratio, how the CPU utilization has changed over time, to see if there's, for example, a background process running continuously that's draining the CPU time. Be able to do logging. That means you experience a problem, you're trying to identify what the problem is. So you look at the system logs. The system logs are actually records of things that have happened. So you can see the errors there. Also, it's very important, for example, if you think that there's a hacker that's trying to exploit your system, you can, for example, go back to the logs and see what has been done, and how, if really someone has attacked, and if so, where the attack first initially started from. Because even if you reinstall whole operating system, if there's a deficiency, it's still there, even if you reinstall from scratch. So you would like to figure out what they have exploited. And debugging information, of course. Such system programs also can format and print the output of the terminal or other output devices. And especially in the case of Windows system, there's also something called registry, as you know. For example, this registry serves like a database for configuration information. So when you install a program, it creates a record for itself in registry, and it can store some information there, like where the working directory of that application is. For example, if you want to save a file, what would be the default directory to save them in? If it has its own libraries, where it can find its libraries, what's the username, and also, for example, to cope against software piracy, most applications put some information in the registry so that if you just copy the program, the registry, since it's separate from the file system itself, the registry does not get copied, so it can figure out that the software can figure out whether it's genuine or just a copy of itself. So typically, if they're doing it, they put such registry records in unexpected places so that you cannot easily find and also copy those registry records. There are system programs for file modification, like the text editors, and also special commands for searching the contents of the files. For example, the grep or find utilities in Unix, or perform transformations of the text, like you can convert text from lowercase to all uppercase. You have utilities for programming language support, like the compilers, assemblers, disassemblers, debuggers, or interpreters. We do have applications or system programs that enable loading the source code either in an absolute address, which means you specifically tell where in memory that program should be loaded, or in most cases relocatable loaders. We'll discuss about the details later, but in the case of relocatable loaders, you can just take that process in memory and put it somewhere else, and still all the pointers will run properly because they're typically pointing in a relative manner. So nothing will matter. So these are called the relocatable codes. So we need relocatable loaders for this. In the case of absolute loaders, it has to be at a specific address, and all pointers typically will be to absolute addresses. Overlay loaders to overlay a couple of programs in memory, especially to be able to share information. Debugging systems for higher level programming languages and also for machine language. We also have system programs for communications between the processes or between the computers. So you can, for example, allow the sender to send messages to another user's screen. You can have a program actually displayed on another user's screen. For example, if you're teaching in the lab, the professor, for example, might start and run the program, but rather than the program running on the teacher's computer, he or she can have it displayed on a user's computer so that the student can see what's going on. Actually, the program is still being run from another computer. That's possible. Web browsing is an example. Email message exchanges, logging in remotely, what you're doing with TeamViewer, or file transfers, either through FTP, CP, or by other means. All these are communications utilities provided by these systems programs. And there are also background services. Some of these they're mostly started at boot time, but you can also start some start, stop, restart, resume system programs also at runtime, but typically at boot time, using some run scripts that are automatically executed when the computer boots. You launch these programs. Some of these programs start in the beginning, achieve their task, and then when they complete, they terminate. But some of them start and remain there as long as the system is up and running. For example, the web service, the HTTP daemon, like Apache, would be started typically by a run script when the computer boots, so that even after a boot, you always have the web up and running, and should always remain running because we never know when a remote user might connect to our website. Similar is true for FTP, SSH, whatever. They typically provide facilities like disk checking periodically, for example, to see if there's a problem in the disk. Process scheduling. This is not the regular CPU scheduling. We'll come to this in more detail later. But for example, you can have a backup process run every night at 3 a.m. to take backups. Error logging if an error occurs, or printing whatever, like the spooler. These can be run in typically in user context. They don't need to be running in the kernel context. So they are part of the operating system, but not part of the kernel. They're in the user context, just running as users. It could be the root user, but pay attention. The root user running a program does not imply the program or the process is running in kernel mode. It's still the user mode, but the root user, not regular user like Tugcu or whatever. Such system programs are typically called services or subsystems, or an older name for these is the daemon, because these are like the demons waiting in the hell, available all the time. That's why it's called a daemon. That's a term coined by BSD Unix several decades ago. And finally, there are the application programs. These are not part of the operating system. They're run by the regular users when you need them. Typically, they're not considered as the part of the operating system, as I said, and they're launched typically either from the command line by just typing in the command, or clicking through the graphical user interface, or if you have a touch screen, by hitting it with your finger, you start these programs. When we are designing operating systems, there is not a single solution that's provided. So I cannot say this is how to design an operating system. The internal structure of an operating system depends on the design, depends on the operating system. So each operating system has a different design. But the best way to start would be by defining your goals, what my operating system is supposed to do, and specifications. What kind of hardware, for example, am I running on? Is this a portable device, or a desktop PC, or it's an industrial PC? How many CPUs do I have in the system? Are they hot pluggable? That kind of stuff. And what's the ultimate aim? What's the use scenario for such a system? You should define the user goals and the system goals. The user typically wants the operating system to be easy to use, easy to learn. It should be reliable, safe, and fast. However, from the point of view of the system, the operating system should be easy to design for the vendor. We would like to make it easy to design and also implement. And yet another thing is, okay, you might have designed a very nice operating system, but how easily can you maintain it? Because you will always have to come up with new patches, because there will be new, for example, hardware provided by companies, so you should be able to support them. It should be flexible, reliable, error-free, and efficient. So when designing an operating system, you should be able to separate policy from the mechanism. Policy defines what should be done. Mechanism defines how it is implemented. So the mechanisms determine how to do something, whereas the policies decide what will be done. So the separation of the policy mechanism is quite important, because with the policy, you define what should be done. So if you later have to change how it is implemented, so if you need to make changes in the mechanism, the policies should not be affected, because other components of the operating system depend on this part. So depend on the policy that's provided by this component. If the policy is heavily dependent on the implementation, on the mechanism, on how it's done, a change here will affect all the rest of the operating system. And just because of a change here, you might have to rewrite everything from scratch. That's something we would like to avoid, as you know, always in software engineering. So for the implementation, there could be, you could use many different languages. Early operating systems were implemented in assembly because you didn't have any other choice. But as the operating systems became more and more complex, other languages were used like ALGOL and PL1. But nowadays, almost all operating systems are typically implemented in C or C++. Actually, even with the modern operating systems, still the very lowest levels are implemented in assembly because that's where you can do all tricks, and performance-wise, that would be the best. But you cannot implement the whole operating system in assembly. That would be very complex and very difficult and would take a very long time. Therefore, the main body of the operating system is implemented in C, typically the kernel, whereas the system programs are implemented either in C or C++. And as you go higher in the systems programs, we make use of scripting languages like Perl, Python, and shell scripts. They're making use of the other programs developed in C or C++. You could use higher level languages for implementation, but such operating systems would be too complex and they would be running very slowly because typically such higher level programming languages are not as efficient as C and C++. The code they produce is typically much larger and they require very powerful hardware, so it's not worth it. One other option is, never forget this, some operating systems, sometimes we emulate the operating systems. For example, if you're trying to develop an application for a mobile device, like let's say a mobile phone, you either do all the coding on the phone, which is quite difficult. Well, you have to at least connect a mouse and a keyboard. You have to work with that small screen. The processing power is quite limited. So instead, what's being done mostly is you develop the whole system on your desktop computer. Say it's running Windows, but you have, for example, an Android emulation. So there is a virtual phone there with a specific version of Android. So you develop in Windows or Linux, whatever. And then when you think you're done, you transfer the executable to the emulated phone, run it there, and see how everything is running. If there are any problems, you go back to the source code in your host operating system, fix it again, and then transfer once again. This is also useful when you don't have the hardware available. Like in the design and development phase of a new phone, you wouldn't have the hardware available yet because the hardware team is developing the device in the next table, so you don't have the hardware available yet. So they would give you the specifications. You first design an emulator for that, although there's no such hardware. While you're developing your operating system and all your applications, the hardware team would be finalizing the hardware, and when they're done, you can transfer the operating system and the applications to the hardware. If the emulator and the hardware are matching each other, there shouldn't be any problems. Of course, there's always slight problems, but typically we are able to fix them. So if you look at some operating system implementations, MS-DOS is the simplest one. We discussed this earlier. But at the very bottom, we have the hardware. It's not shown here in the figure. On top of that hardware, we have the device drivers available in the ROM and ROM BIOS. So on top of that, there is the MS-DOS device drivers that are running. There could be some resident system programs. For example, for the case of the Turkish keyboard, the original MS-DOS would be supporting only the US keyboard. So for the specific Turkish characters, like the Turkish characters like Ch, whatever, they're not implemented in the keyboard device itself. This is just in the software. So the keyboard would just be sending the same signal actually to the operating system, but we would load what we call a resident system program, which would capture those keystrokes and say, rather than a closed bracket, I'm going to use the Turkish character U for that, U with umlaut for that. And for the open bracket, I will use the soft G character rather than the open bracket, whatever. So this way, actually for the same keyboard hardware, you were able to use a different keyboard layout as you wish. So that would be what we call a resident system program. Resident because what we do is when we start the computer, we run a software called KEYB for keyboard and give some parameters actually specifying the code pages for that language. So it knows how to treat it. Now that program, when you run that keyboard program, has to terminate because MS-DOS was a single tasking system. If it always continued, you wouldn't be able to run your applications. So it terminates, but when it terminates, different from the regular programs, it does not release the memory. It remains in the memory. So what that program actually does is it loads the functions to some specific space in memory, and the program terminates, but the functions remain there. So every time you press a key, that function is actually throwing a hook at the signal that comes from the keyboard and translates it to Turkish characters. That's how our applications would be running. My application would be the sole program running actually in the system. But while it's running, the input would be always passing through this resident system program. So that's how the MS-DOS system was running. Unix has a more complex structure. As we discussed, we have the system programs and the kernel. So the kernel consists of everything below the system call interface. So everything implemented by the system calls and anything above the physical hardware because that's the hardware. So it provides utilities like file system, CPU scheduling, memory management, and other operating system functions are provided by the kernel. Remember our discussion about scheduling, whether it was part of kernel or not? Pay attention. CPU scheduling. There are different kinds of scheduling. CPU scheduling is part of the kernel, as we mentioned last time. Other types of scheduling, we will talk about them later, but CPU scheduling has to be in the kernel because it's the kernel that decides which process should be running. If it was not in the kernel, we wouldn't be able to do the context switches. Anyways, the traditional Unix system is a layered structure. So at the very bottom, we have the hardware. For example, we have the terminals. The terminal means the keyboard and the monitor. So for the terminal, you need a terminal controller. Or for disks and tapes, whatever, you have the corresponding device controllers. For USB devices, you have the USB controller. For physical memory, you have the memory controller. So all these, the bottom layer here is the hardware. The hardware connects to the kernel through the kernel interface to the hardware, and the kernel provides to the upper layers the system call interface to the kernel. So anything in between is the kernel, like handling the signals terminal handling, character devices, I/O system, the terminal drivers, file system, swapping, block I/O operations, disk operations, tape drivers, CPU scheduling, page replacement when we talk about paging and virtual memory, demand paging and virtual memory. All these are related. We'll come to these by the end of the semester. Now, all these are the kernel, and the kernel provides services to the systems programs and also to the user applications through the system call interface. So in the system programs, we have the shells, the commands provided by the shell, compilers, interpreters, the system libraries, and all we have just discussed in the previous slides. It is also possible to have a more layered approach. This is similar to the previous case, except that you have now n layers. At the very lowest layer, at layer 0, you have the hardware, and as you go up, each layer provides services to the upper layer, and the upper layer benefits from the services provided by the lower layer. Again, we have a modular design. Now, there's also the microkernel system structure approach, which is used by, for example, Mac. Mac is used by the Darwin kernel of the Mac OS X system. As the name implies, it is a very small kernel. That's why we call it the microkernel. So the kernel this time has limited services compared to the previous case in the case of Linux. Remember, in the case of Linux, we were providing all of these services in the kernel, whereas in this case, we have only the basic services that are provided by the kernel. So the kernel provides now, the microkernel provides now the interprocess communication, memory management, and CPU scheduling services. Above, all of the other system services are provided as separate modules which need to communicate over the microkernel. This requires that you switch from the application or file system or device driver, it doesn't matter. In all of these, you're in the user mode, so you need to switch from the user mode to communicate with the other module to the kernel mode. From the kernel mode, go back to the user mode, get the response, again switch to kernel mode, and finally again return to the user mode. All these switches between the kernel mode and the user mode constitute the drawbacks of this microkernel design. However, it also has its benefits. The most important thing is the microkernel is very small. Since it's very small, you can easily extend it. You can easily make modifications on it. If you change, for example, the hardware, you can easily make modifications in the microkernel to adapt it to the new architecture. And since it's small, you can design the microkernel to be more efficient, reliable, and secure. So these are the advantages of the microkernel structure. In modern operating systems, we typically have the concept of the loadable kernel modules. Now, one approach is you can put everything in the kernel, okay? But if you do this, now, first of all, what do you mean by everything? For example, consider the scenario where, for example, you have a Linux system and you may need to connect an external disk, for example, a USB disk, say formatted for the NTFS file system. Well, that means in the Linux kernel, to be able to read and write from a Windows disk for the NTFS file system, you should have the NTFS support in the kernel, which means the kernel should get a little bit larger. You have to put all the code necessary for doing the operations with NTFS. You can also have different types of disks you could connect to the system. So the Linux kernel developers will have to support all types of file systems. They have to support NTFS, they have to support VFAT, they have to support X3, X4, RiserFS, and all others. Now, probably you will not be using any one of these, or maybe one or two of these. But since the designers do not know which one you would need, they will have to put all of these to the kernel, which will make the kernel too large, too heavy. Remember, the kernel is always in the memory. It will consume a lot of memory space. And also, more important thing is, the kernel is so large, it's such a big chunk of code that the probability of making errors, causing bugs in the kernel, gets larger because you have all these different types of code. So why not have a bug somewhere? So to avoid this, what we do is, now, the core of the kernel has to be there. Like you should always have the CPU scheduler. You should have the basic I/O operations. You should have this and that. But anything that is fancy, or maybe not fancy, but anything that could be optional, we would like to make them separable modules, separate modules that can be loaded only when necessary. So the kernel has these not in the kernel itself, but as separate modules. If needed, they will be loaded. If not, they're not in memory. Okay. Now, in this case, if you never connect a, say, NTFS file system to your computer, it will never be loaded. If you connect an NTFS file system, now before mounting that external disk to your file system, mounting means attaching, making a part of it. In other words, visible, accessible. Before making that external file system accessible, first the kernel has to load the corresponding kernel module, in this example NTFS module, into the memory, and then it can attach that external device. Now that means when you insert the USB connector for the disk, you will not see it immediately. Probably it will take a couple of seconds for the operating system to detect that that device is an NTFS device, find the NTFS module, load it from the disk to the memory, and then using that module, mount the external device into the operating system's file system. Now, this takes several seconds. Therefore, when you attach the USB connector to your computer, it might take several seconds for the file system to be visible. Now, interesting enough, if you unmount it, detach it, or eject it in Windows terms, if you eject the external device and then immediately attach it once again, you might realize that it gets mounted much faster. And the main reason for that is when you detach it, when you unload that module, actually, when you remove that device, typically the kernel probably, I cannot guarantee that, but in most cases, it will keep that module in memory until it needs the memory space for that module. So you don't immediately remove a module as soon as it's not needed. If somebody needs that space, you move it. But if not, no need to bother with that. Okay, so it is possible that when you connect once again the USB cable, it will find the loadable kernel module already loaded to the memory. Therefore, it will run faster. Such kernel modules are typically implemented in an object-oriented approach. Each component, as I said, is a separate module. And the reason for that is, as the designer, I don't know which modules would be loaded in your computer system, in your operating system, when. For you, it might be one case. For your friend, it might be another case. So the designer cannot know that. So the modules should be designed as separate entities so that you can have any combination of these modules installed and running at any point in time. These modules interact with each other through known interfaces like USB 3, HDMI, whatever, all these interfaces. And each is loadable within the kernel only when required. This layered approach with loadable kernel modules is used in Linux, Solaris, and similar operating systems. By the way, the term Solaris is yet another brand. Actually, there used to be a company, a very successful company by then, named Sun Microsystems, and they developed one of the best Unix flavors, actually, named SunOS. SunOS in time was renamed as Solaris. It was really a very successful Unix brand, but it was proprietary. That means the source code was not open. In time, Sun Microsystems decided to open the source code of Solaris, in other words, convert Solaris to an open project. So they named it Open Solaris. And they had a quite strong community support. However, later Sun Microsystems was acquired by Oracle. So Oracle also acquired the Open Solaris project. And in time, Oracle changed its mind and converted Open Solaris back to a proprietary project, which means Solaris was not an open source project anymore. Later, they also renamed the operating system, but it's not popular anymore, and still it's a proprietary system where only Oracle customers are using. So the design for Solaris was you have a core Solaris kernel, and all the others were actually separate modules that could be, some of them always used, some of them loaded when necessary. Well, in reality, if you look at the modern systems, you will see that what we have discussed is not like you either use this or that, but typically we have hybrid systems. That means you make use of multiple of these approaches to achieve better performance, security, and usability. In the case of Linux and Solaris, the kernels are what we call monolithic. That means the kernel is one piece. So you compile the kernel, especially in the case of Linux, since it's open source, you can configure the kernel as you wish. You can say, I'm going to make these built-in and these as loadable. For example, if you are going to use, say, an NTFS system all the time, you might say, why do I make the module and have that overhead? Let me just put it inside the kernel, so make it built-in property, because I anyways have this NTFS system mounted all the time. Okay. Whereas for some others, you might say, well, I'm not using these functionalities, or I don't have such hardware. So you can completely remove them or make some parts loadable when necessary. In the case of Windows, Windows is mostly monolithic. That means everything is actually inside the kernel, but they also provide some microkernel support for subsystems to allow for personalization. In the case of Mac OS X, which is the operating system of Apple computers, they have a layered approach where the user interface is called Aqua. It's one project. The user interface is one project named Aqua. The programming environment is yet another project named Cocoa. And for the kernel, they're making use of that microkernel of Mach, and also they're benefiting from the some components of the BSD Unix Berkeley socket distribution flavor of Unix. They also have some additional I/O kits and dynamically loadable modules, which they call the kernel extensions. So that would be the end of this chapter. Please read the assignments listed here. Note that these numbers are, as far as I remember, for the 9th edition of the textbook. So if you're using the 10th or another edition, the numbers could be different. But the topics should be the system calls, types of system calls, and the operating system structure.